Hi, my name is Justine Harkness, and in this video, we're going to look at how to predict how a directing group will affect the rate of electrophilic aromatic substitution reactions, focusing on the general trends for electron withdrawing and electron donating groups. In addition to grouping substituents based on how they direct subsequent groups to the ring, we can also group them as activators or deactivators based on how they affect the reactivity of the benzene ring. Activating groups will increase the reactivity of the ring by donating electron density. If we look at some of the trends that we see in this table, of course, we're starting with electron donating groups. For our best donating group that we have here in amine, we have a lone pair that we can donate to the ring via resonance. The same is true for oxygen-containing groups as well. Note that nitrogen-containing groups are better activators because they're less electronegative, so they don't want to hold on to that lone pair as much as oxygen does. We also have R groups, alkyl groups, like a methyl group. And as we had discussed in other videos, methyl groups and other R groups do donate some electron density, and we see that also with carbocation stability. We donate electron density to stabilize carbocations, just as we can donate some electron density to increase the reactivity of a benzene ring. Finally, we have aromatic substituents. These aren't as activating as R groups because donating electron density will in some way affect the aromaticity of the ring. So in general, these electrons like to stay localized to that benzene ring that they are on currently because they are currently very happy. Aromatic molecules are very stable, so we don't want to break that aromaticity. On the other hand, we also have our electron withdrawing groups, and these are in general meta-directing substituents. We do see one exception to this general trend of ortho-para directing being activating and meta-directing being deactivating, and those are the halogens, and we'll be looking at why they are an exception to this rule in a later video. But let's focus on our electron withdrawing groups. So let's take a look at some of the general trends. And here we are going in increasing deactivation here. So at the very top we have carbonyl containing compounds, which would be these first four in this table. Now, the carbonyl itself is polar. We have a partial positive charge on that carbonyl carbon, of course, partial negative charge on that carbonyl oxygen. And one way we can make a carbonyl even more electron withdrawing is to add increasingly more electronegative substituents to this X position. Next, we have the cyano group. Now, if we look at the difference between the carbonyl and the cyano group, we see here we have, two bonds between our carbon and our oxygen. In the cyano group, notice we have 3 bonds between the carbon and the nitrogen. The way I like to think about the number of bonds is kind of like a highway for electrons. If we have a double bond, that would be kind of like an interstate where we can be pulling a pretty nice number of electrons. But if we have a triple bond, this is like the Autobahn where everyone's really flying. So we can pull more electron density through a triple bond, which makes this a better electron withdrawing group. Finally, we have at the very bottom the nitro group, our best electron withdrawing group. Notice that the nitrogen has a full positive charge, and we also have a pulling of electron density from both of those oxygens. So that's going to make this group want to pull electron density from the aromatic ring to which it is attached. So just to sum up these general trends, and we have an activating group or something that is electron donating. This will increase our reactivity by donating electrons to that conjugated pi system. That makes benzene more nucleophilic. Remember, nucleophiles are characterized by the presence of electron density. So if we give more electron density, we're going to make it even more nucleophilic. In addition, we do have a carbocation intermediate for electrophilic aromatic substitution reactions. So donating electron density to the ring can help to stabilize that carbocation intermediate. A deactivating group is an electron withdrawing group. These will always decrease our reactivity by pulling electron density from the ring and making the benzene ring less nucleophilic. Less electron density means less nucleophilicity. Additionally, because we're pulling away electrons or pulling away negative charge, this will destabilize the carbocation intermediate, which will make this reaction occur more slowly. So let's apply this with a practice question. Now here we have to rank these directing groups in order of increasing reactivity for electrophilic aromatic substitution reactions. So the first thing we can do is to classify each of these as either an electron donator or an electron withdrawer. So if we look at our amine, we have a lone pair of electrons on that nitrogen. This can donate electron density to the benzene ring, so this would be an electron donating group, thus an activator. Looking at our next group, notice we have a sulfur attached to oxygens. Those oxygens are going to pull electron density away from that sulfur, giving it a partial positive charge. And that's going to make it a good electron withdrawing group. Going down to our carboxylic acid, again, we have carbon that is bound to two oxygens. Those oxygens are going to pull electron density. We're going to have a partial positive charge on that carbon, so this will be an electron withdrawing group. And finally, a methyl group, well, it doesn't have lone pairs that it can donate to the ring. It can donate just a little bit of electron density, so that would make it a good electron donating group. So we're looking at increasing reactivity, which means we have to go from the best electron withdrawing group to the best electron donating group. Now our best electron withdrawing group that we have here would be B, since those oxygens will pull a lot of electron density from that sulfur, and that would allow it to pull a lot of electron density from the ring. Next, we would have the carboxylic acid, also due to the ability to pull electron density from that ring with that partial positive charge. Next, we have the methyl group. Doesn't have a lot of electron density to donate, but can give a little bit. And finally, our best electron donating group would be the amine for that lone pair of electrons. So as you go back and practice more with this, focus more on the general trends that underlie this concept rather than using a blunt memorization approach for that ranking.